So we run first our script and then run our um, our probability and frequency table. Here we have this train DF and the valid DF. That's the variable that will hold all our train and test set using a random state. So we create this train test split delays DF. Test size is 4 and then the random state is 1. Then we have the precision, we set the precision to 4. Then we print now the probabilities of each flight status. So here, the result will be for on time. The result of this is that for on time, the probability is 0.8023. And for the delayed, the probability is 0.1977. Next, we have to print the frequency table where we can see each of the predictors probabilities. So we use this. This is actually a loop, and then we print all of the predictors and we print their probabilities using this frequency table command using a pivot table. And here we specify that the index is the flight status because usually this is our outcome. Okay, and the columns are the predictor. And then we divide each row by the sum of the row to get the conditional probabilities. And then we print the probabilities table. So we have this. The result of this loop is the each of the predictors are printed. These are the day of the week, the CRS departure time, the CRS departure on a, this is the continuation of the CRS departure time. We have the origin, the destination, the carrier. Those are our predictors, and then each values are printed as well. So the days of the week, there's the 1 for Monday, 2 for Tuesday, 3, 4, 5, 6, 7, and so on. And the flight status values are delayed and on time. So it will print the probability of a delayed flight, no, for Monday, that is 0.1916. For Tuesday, that is 0.494, and so on. So if you can observe that there is the larger value here is the for the delayed is the zero point 0.1. Among this, the largest probability is 0.1916. That means that there is a higher chance that the flight is delayed on if the day of the week is Monday. And there is also a higher chance of an on-time flight if the day is Thursday. And for the departure time, there is a higher chance to get a flight to be delayed if the departure time is 8 o'clock. Of course, that's a busy time. And it will be on time. The higher chance for it to be on time is if the there's more here for the departure time. The highest is there's more higher probability here, which is this the 15, or if it's 3 o'clock, 15 is 3 o'clock in the afternoon. And for on time, you have the higher probability is 0.1171, also 3 o'clock. Then based on the origin, the it's more there's more higher chance to be delayed if it's coming from DCA. If the origin is DCA. And we also have if it will be on time if it's also from DCA. Okay, the higher chance to be delayed according to destination is if its destination is LGA, and on time as well if it's zero point 0.5, or if it's from LG, or if its destination is LGA. And it will be there's a small probability for GFK for both delayed and on time. For courier, you have the DH, and for the delayed, for on time, you have the DH as well. So that's how you print uh, all the probabilities for each predictors. Next is if you want to specify the probability of a specific value, we can use this command. For example, you want what is the probability of the the carrier is DL, the week is 7, the departure time is 10, and the destination is LGA, and the region is DCA. So first you'll have to get the p hat delayed, the probability for it to be for the probability and for the delayed, and that is 0.0958 times 0.1609. So the this is coming from the frequency or the probability table. You have carrier is DL, so you have this carrier DL. For the delayed, it is 0.0958. So that's, you get the 0.0958. And for the day of the week is 7. Day of the week 7, the delayed is 0.1609. And then for the departure time 10, you have 0.0307. For destination LGA, you have 4215. And for origin DCA, you have 5211. And then you have 1, 2, 3, 4, 5 predictors. So you have 1, 2, 3, 4, 5. And then lastly, you have to set the 0.1977 for the delayed probability of the delayed. And then we also have for on time, the same process for carrier DL. For day of the week is 7, and departure time is 0.01519, LGA 0.5779, origin is DCA is 66478, origin DCA for on time is 6478, and then for on time you have the 0.8023. Then we print it. That's we call it the p hat delayed. So this is the p hat delayed, and this is the p hat on time. So these are their p hat. So the p hat is just a temporary, or it's the numerator that we discussed in the introduction a while ago. It's the numerator, and it's used to actually compute for the probability. So the actual probability of having a delayed flight with the specific data, such as this one that we specified, if the carrier is DL, if the day of the week is 7, the departure time is 10, the destination is LGA, and the origin is DCA, the actual probability of these values, that the flight status will be delayed, is 0.058. And for it to be on time, the probability is 0.94. So, in conclusion, therefore, that given this data, the, there is a higher chance that it will be on time. Next, let's add a new code cell, and we now want to create the actual and the predicted value. Okay, so here we copy this and paste. So here we will score. This is how we score the data using naive Bayes. So it will show us the predicted probability and the class for the example flight, and which coincide with our manual calculation. So we run this. Now we have the result is that we have the actual is 0, and the predicted is 0, and we have this for we have this actual prediction, or the probability of on time is 0.058. 0.942011, and for the delayed you have 0.05989. So these are the same with our manual. This is actually the manual calculation. Okay, this is the manual calculation, and then we can also use this to show the actual probabilities of the two. So to do this, you or to use this code instead of using the manual coding that we used here. You will just use the pd.concat and then create this labels, actual and predicted, and then you have to specify here what are your predictors or specific data for the predictors. So in our example, we want to specifically identify the probability for carrier DL is equals to 1. This is what we specify here. Okay, this is what we specify here in our reviews or manual calculation of probabilities. So the carrier DL equals to 1. Okay, and day 7 equals to 1, and for the carrier D is DL, and the day 7 is 7, days of the week is 7, the CRS departure time is 10, and the destination is LGA, and the origin is DCA. So it will print, this is the index of that specific record, and then it will show us that the zero here means that zero here is on time, so meaning the actual data is on time. This record in the data set, if you look at this record in the data set, its actual value is on time, and the naive Bayes predicted it to be on time, 0. So there is a probability, its probability to be on time is 0.942011, and delayed is 0.057989. Next, let's add a new code cell. Here we print the classification or the confusion matrix. So confusion matrix will show us the summary of the accuracy of the prediction. The accuracy of the prediction. We use the classification summary command and then print. So we have this result, the accuracy overall of our naive Bayes prediction is 0.7955. That means it the classifier ran through all of the data set and they predicted all the rows there, and then the actual flight status is compared to the predicted flight status, and the accuracy of those prediction is 0.07955. So for this is now the detailed prediction. So there's on time is the actual on time is 988, and delayed is 61.